Alright, we're back again. Why does this is not right. Okay, adjust the camera. So previous video we were trying to work out what VB was from this particular simple circuit here, which is me trying to work out something about transistors, but it's kind of a bit removed from transistors. But anyway, we're going to continue on. So we did the complicated way of doing it, which is giving me an equation that looks like this. And I had to do lots of weird algebra that I didn't want to do. So is there an easier way of doing it? And yes, there is. So this is, I don't know exactly how you say it, it's Thevenin's Theorem. So this makes it a lot easier, I think. And so this is a neat little process, which doesn't, when I first saw it, this is like, well, that seems neat, but I don't know if I'm going to, what's the, you know, it's nice to actually use it for something to see what the point is of it. But the idea here is that if you have any sort of linear circuit, so basically if you have a circuit full of things that are resistive, and nothing too complicated, but just resistive stuff. So this here is a lot of different resistors, and they're all going all over the place. And then they're meeting up with the rest of the circuit over here, which is like, you know, your other part of your circuit. So we're trying to turn. Right. This is where the rest of the circuit meets up with this circuit. So you have to have two terminals. This is A and B. This Thevenin's. I keep wanting to put an M there, Thevenin's or something. But we're not going to. So the point of this theorem is you can actually turn any kind of circuit, no matter how complicated it is, with as many resistors as you want, in whatever sort of arrangement or particular complicated arrangement that you can do, and you can convert it to a simple circuit from the point of view. So you're not really saying that you can just turn all of this, well, at least I'm not going to say it here, that you can turn all of this into something that just uses one resistor and the voltage source. But you can say from the point of view of the circuit that's connected to A and B, you can substitute in something and it will appear to be the same. They have the same sort of characteristics. So I've used here a circle with a plus and a minus to mean a voltage source. So you can convert this into one resistor, which is not a resistor that's actually in here, and a voltage source, which may not be the same voltage source as this voltage source. So this voltage source might supply 10 volts, but your equivalent circuit one might actually provide like 5 volts or whatever. It's not going to be the same as those two, unless you start off with a circuit that looks exactly like this, and obviously it's going to look very similar. So how does this process work? Well, you have to work out two things. You have to work out the value of this resistance, and you have to work out the value of this voltage source. And you can kind of, like, I don't know, I haven't gone, I thought maybe I could go through a proof of why this is true, but you can kind of get a feeling that you can turn all these resistors into a single resistor if you think about it, because you know that if you have two resistors in series, then you can add them up and you just use one resistor with the same value, with the value that's like the two added together. So if those two were in series, you could replace it by one resistor with that value plus that value. And if they're in parallel, it's a slightly more complicated equation, but you end up getting a single resistance to replace two other resistors. So given that you can replace parallel and serial things, you could eventually turn this all down into one little resistance. That's all I'm going to talk about for why it works. But let's just say it does work, and it does. So what we're going to do is we're going to take my circuit that I've got here, and we're going to try and make it a little bit simpler. So we're going to use this, I'm going to have to keep it here, Thevenin's theorem, all right, to turn this circuit, where A and B, so remember that I'm kind of interested in what the voltage is here, and this is going to be ground. Right, so I'm kind of interested in this. I can kind of like chop this bit off, or I can say, well, turn this circuit into something else. I don't care, as long as it has the same characteristics, and then connect it up to here. And because I only really care about what the voltage drop is across this bit here. That will give me what VB is, which is what I'm trying to find from the previous video. So that VB is the voltage across these two components. So I want to turn it, I want to reduce this down with Thevenin's theorem to a simple circuit, which will look like this. So I'll have my Thevenin's voltage across here, and then I'll have my Thevenin's resistance here, and then I'll have my my remaining bit of circuit, which is this one here with my RE. So this is still going to be, I didn't write it in, but that's still going to be RE. Because this is my little bit of circuit that I care about, and I'm trying to turn this into this for the point of view of here. Because if I have done this, it becomes a lot easier to work out what this is, because they're all in series, and as you can see, as you will see in a second, it will be a lot easier to calculate what the voltage is across this section here, if this was the circuit that we had. So the question becomes, how do we turn, we're going to do a very, very, very simple example of this, how do we turn this into that, kind of? That's what the next page is for. So the first step is we have to calculate the voltage at the load terminal. So in this case here, I'm going to call this my load, and this is like the source part of the circuit. So I want to work out what the voltage I see at these terminals here. This is an easy case. It gets slightly bizarre, like where I find it slightly a bit weird. If there happen to be, I'm not going to draw it, I can't draw on it, can I? If there happen to be a resistor in here as well that isn't part of the load, it makes it. I'll explain that in a second. But I should probably leave it for another video instead of trying to explain everything in one go. But basically I want to work out what the voltage that I see between these two terminals is going to be given the circuit here. And that's not too hard, because this is just basically a straight voltage divider thing. So this is the ground here, this is like 0, and then we've got the supply voltage coming in here, and we've got a resistance here and a resistance here, and so the resistance, the voltage, is going to be the ratio of these two resistors times the voltage supply. So that's just a standard voltage divider circuit. So in this case here, it's going to be the resistance across the resistance across here times the total resistance across here, across the both of them, multiplied by the supply voltage. So that gives me the ratio of voltages across, what am I talking about? How am I going to explain this? The proportion of the voltage that goes across this resistance. So just another reminder, if this was 100 ohms and that was 50 ohms, you would think that most of the voltage has to be spent going across the 100 ohms. Well, 2/3 of the voltage will be spent going across the 100 ohms, and 1/3 across the 50 ohms. And that will come out here. So in that case here, I would have 100 over 100 plus 50, which will give you 100 over 150, which is the same as 2 over 3. So that will be 2/3 of the input voltage in that case. So that's how we can work out what that is. So we know what the Thevenin, see I did it, I said min, Thevenin's voltage is going to be worked out with this equation here. I feel like I didn't explain that too well, but that's okay. So second part, different from the first. So now we're going to calculate the Thevenin's resistance. And in this case here, we have to calculate the resistance between these two things, between the terminals, after we've disabled the supply voltage, or we've disabled the I'm trying to think, the thing, because you have to disable the current. You can do this with currents, but I don't think we're going to do that with currents. Forget what I just said. We have to disable the voltage sources, and we disable them by substituting a short between them. So we just take them out and put a line through it. So they don't break the circuit, they just disappear. So the voltage source has disappeared from here and it's been replaced by a wire. And so now we have to find the resistance between these two things, given that, just looking from that point of view, looking from A and B. And it seems a little bit hard to think about it when I look at this picture here. So if you just rearrange it slightly, so you have to think, is this the same circuit as that one? Well, it is the same circuit as that one. So A comes in and it splits off between RA and RB. I feel kind of now calling this RA and RB not the best thing, given that I've called the terminals A and B. But these are two different A and Bs. It's not the same A and Bs. They don't have any relevance. So what are we going to do? So yeah, so you can see here we go here. It splits off to R and to RB and RA, RB, RA. Goes through both of them. So it goes through that path. Goes through that one, links up again, goes to B, which is what happens here. So it's the same this is the same circuit basically. And if you look at this circuit, then it should be pretty easy. It's just a standard parallel resistances in parallel. So 1 over RT, which is the resistance through here, is going to be equal to 1 over RA plus 1 over RB. So RT equals RA times RB over 1 RA plus RB. It's just a sort of standard formula. You can work it out from that, or you can just know it off by heart. I worked it out from that. This doesn't work if there's more than 2 resistances. There isn't a nice simple theory for that equation. So now we have 2 things. We have our Thevenin's voltage and our Thevenin's resistance, which is that and that. And so now we know what this is. Now we know what this is. Now we know what RE is. So we should, in theory, so we'll turn this into this. I should probably write. So in this case here, that's VS. So I can't write an S upside. Is that an S? Probably an S. V5. Remember that this voltage here is not the same as that voltage there, so they're not equivalent voltages. But you're still going to get the same answer. The whole point of this trick is that you're going to get the same answer for what you're looking for here, because that's just the way it's going to work. Right, and so the last bit we have to do is this again is just another voltage divider, but we've got this diode in the way, so we have to take that diode away from the input voltage or the supply voltage, but this is the Thevenin's supply voltage. So what we end up with is VB will equal RE divided by RT plus RE. So this is just the ratio of voltage across RE given RE and RT. So as we go through here and we use a certain amount of voltage to go through both RT, ignore the diode for a second. We use a certain amount of voltage to go through RT and RE. We're dividing that up. So this is just me saying, well, what's the percentage of that? What's the ratio? What's the fraction? This is the word that I want. What's the fraction of the voltage going between these two that's going to be going across RE? And the voltage that goes between those two things is the total voltage minus 0.7 for the diode. But then to get VB, once we've worked that out, we have to add back in that thing that we dropped across the diode. So that we're going to add in 0.7 at the end. I hope that kind of makes sense. And so I think that's it. So that's a lot easier, and I did work with it. This does give the same answer in both cases. So that's exciting. So it looks a lot nicer. But I mean, this is kind of a little bit, facetious. I don't know. Like, I feel like when you write it like this, of course you have to work out. Where did I put the thing where I have to work it out? You still have to work out this. You're still having to do. And I did actually do a bit more where I went through and I expanded this out and tried to get it. Because, you should be able to get them back to be the same equation. So I should be able to expand this out and eventually get back to something that looks like this. Because they do match up and they give the same answer. And you can, I kind of got somewhere, but then I got bored and gave up. So it gets kind of messy. I'll leave that as an exercise for the reader. But of course, that looks really simple in comparison to that, but then you still have to work out that and that. Sorry, that and that first. But that's okay, because this is a nice way of conceptualizing it. It lets you break these things down into nice small bits and work it out as you go along, and you can work out the other bits as little nice small packets. Well, I can work that out, and then I've got it, I've written it down, I've stored it somewhere on my computer, and then I've got that one, I've put it somewhere else, it's still on my computer, and we're all done. So I thought it was neat and tidy and fun, and it works, and so that was good. Maybe we should just for a bit of practical stuff, we've got 13 minutes left. Let's just test it out and see if it works. I've only got big thingy whatsits today. Where did I put the little supply? So in these ones here, by the way, these larger boards, they don't. Oh no, this one does. It's got a little red line that goes all the way across. I could swear that they didn't. I could swear that they've got a break in the middle. Okay, well if they do have a break in the middle, because they normally do, so that's a bit weird, but the line's going, oh, it doesn't matter, it doesn't matter. Well, we can always find out another day, but you can put this in the middle and then it's all fine. So that just goes there. And that links the two together. So these are 1000, but I don't want those. Where did I put my little book? Alright, so anyway, I wrote down a couple of examples and the answer. So, according to my equations, if RA was 10k and RB was 5.6k and RE is 1000, then RVB is going to be 0.8603. I didn't think, I'm not too sure, I think I actually used a voltage drop of 0.6 to get there. So when I put this, the other thing is, when I put this into that online circuit simulator tool thing, it uses a much better model of a diode, and of course the voltage drop across a diode is not constant. It varies with how much current's going through it, and so a lower voltage drop will allow some current through. I was going to draw a picture of what it looks like, but there's a little graph. We can do it. It looks kind of like, can I do it upside down? So it looks something, I don't think I can actually, to be honest. It looks something like, I'm going to guess, like, I think I got that the wrong way around. So this is the voltage V, and that's current. So as we get to here, so this is about 0. I can't do 0. It's like 0.7 volts there, but this is like 0. So according to the, and my point was, according to the simulator thing, actually in all the circuits that I was testing, you're only getting like a voltage drop of about 0.55 volts across this, because the current actually turns out to be so low. But anyway, these are 10Ks. So I think I have everything sitting on the table all ready to go, except I don't know where the 5. Alright, so here's a diode. Alright, so let's just do it then when they're all the same. So we're gonna do 10Ks. So this is going to be my VE. That one's going in there. I don't know if this is exact, but I feel like I should do something that involves putting wires on a circuit board, because that will be fun. So I worked these out just by making a computer program and then just plugging in different values. So I would like to use a proper model of a diode, because one day I'd love to work out or develop my own little circuit simulator tool. They won't be as complicated as other ones, but just that way it's a good way of learning how things work. So if you can make a reasonably good tool that can predict the behavior of reasonable circuits, then you've really learnt something, haven't you? And that's the best way to learn. But I think I'm a very long way from here. So we're going to start off, and in this case I'm going to bring it up close so people can see what I've done. So I think at this point you can just put the video and not watch. But these are all the same. These are all 10Ks. So this is my RE. It's going into. Well, here's the picture here. So RE. Oh, this is RA. Sorry, what am I talking about? RA is coming down here, and then we've got a path that goes through a diode into RE, which is this one here, and then another path which is going through RB, which is that one there. So according to my maths, when they're all the same and you have 5 volts, I'm kind of like not entirely sure. It should be like 1.867, which is not a really good value because it's pretty close. So if they were all the same, then you would get like half the resistance going between. So if there wasn't a resistor there and these resistors were both the same, then you'd get basically that would be the same as half the resistance going through here, and so then you get this 2/3 going through this, 2/3 of the voltage going through here and 1/3 of the voltage going through here, and so the voltage would be something like 1.667. So it's very, very close, isn't it? So I don't know if my meter is going to be able to say if I get it right or not. But we'll set it for 2 volts, and we'll turn this thing on. So it's a regulated 5 volt. So this is nice because it all kind of works so that everything's that you have a regulated voltage. It wouldn't work if you're running at 5 volts from a battery, because would it? No, it probably would. No, it probably wouldn't. Okay, it doesn't matter. All that matters is we're going to find out what this thing says, and it says, I'm almost too nervous to do this. It says a voltage drop of 1.799. Is that on the camera? I think it is. I'll turn the light on. Alright, 1.799. Which is pretty good. Like that's roughly close to 1.8. Well, it's closer to that than 1.667 is. So that's okay. And of course these aren't perfect. And of course I don't know what the voltage. We can just test what the voltage drop is actually across. So in this case here, the voltage drop is 0.5 volts according to this thing. So that's actually a lot lower than what I was thinking. I think I used 0.6 in this equation. Should have written that down on the piece of paper. So, you know, not too bad. And we can kind of see, actually one more thing, we better quickly do this. I'm not going to bother doing any other resistance values. So, but the voltage drop across this one is 1.8, which makes sense. And the voltage drop across this one is 1.300. So, well, this makes perfect sense. So that adds up. So they do have a different, but my main point here, so we have to go back to what I was originally confused about in the stuff that I've been reading, is that they say that when you have this sort of biasing network, this voltage here is sort of fixed, whereas if you take this thing away, if you take the input away, then the default voltage is set by the voltage divider. But in this case, that's not true. So if that was the case, then you would expect to see a voltage here of 2.5 volts. So you expect VB to be 2.5 because this part doesn't have anything to do with it. We probably should try actually just using an actual thingy. What's it? Because I'm going to say in a second exactly why. I've got a thingy what's here. I always forget which way. You'd think by now I could remember which leg is the. Alright, so collector, base, emitter. So I could replace the. I'm gonna take the collector leg and I'm gonna stick it out to the side. And that's the base and the emitter. Poor little transistor is going to have a bad day, and then we're going to take that out and we're going to replace it I'm just going to say why this doesn't actually work when you're using it as a transistor. But let's just see. So that should kind of act like a diode at the moment. So this is a little 2N222, and I've taken away the collector leg, and I've just used the base to the emitter thing. What do we get there? We get 0.6. So we've got a voltage drop of about 0.65 volts there. So that's kind of closer to 0.7 volts. And then we've got, so that's actually almost spot on with what we were predicting, isn't it? So if you do that with a transistor, it's 1.847 compared to my predicted 1.867. So not too bad. Not too bad. So using a diode does make sense. But of course, yeah, so that's not what I get confused when I read it in the thing. But of course, I've got a bit more to do, which is this is not a diode, this is a transistor. So things are going to work slightly differently. And I think what they actually mean is they're kind of talking about the Thevenin's voltage here, and not the actual voltage that you get like at any point that you're testing it. Well, I'm going to come back to that once I fully understand this. But of course, what's going to happen before we just finish off is if you actually had the collector hooked up and there was current flowing through here, then there would be current flowing from this part of the circuit through here and into here, much more current flowing through here. So the current that goes this path is going to be much smaller than the current that comes in from the collector. So the current at the emitter is the base current plus the collector current. So when you add that in, the voltage drop across the emitter is going to be much, much higher because there's much more current going through. So V equals IR. If you've got more current, then you're going to have higher voltage. So that's going to give you a different value. So once I've got this part worked in, then you're going to get quite different things. So this is not a very good thing, but I just thought it was interesting to talk about it. So I hope somebody learnt something from that or found that kind of interesting, and one of these days I'm going to feel really confident to explain this circuit and how to get to it, and the basic physics behind all this stuff, and hopefully that will be interesting. But I have to work through it my own little way in my own time. And read over things many times until I get exactly what's going on. And we're getting there. We are getting there. So one day. But thanks for watching, and there'll be more videos on this channel soon because I'm going to start being more productive. So thanks for watching, and bye.